Before we start actually studying chemistry, we have to come to some agreement about how we're going to measure data, how we record that data, what units we use, how we represent the numbers that we record for the data. And that's going to be largely the subject of Chapter 1. We're going to start in this section by talking about the units that we're going to use to measure things in chemistry. We're going to start by considering what we call the SI system of units. SI stands for Système International, which is just the internationally agreed upon system of units used in all of science. The fundamental point of the SI system is that there's only one SI unit for any physical quantity. Okay, only one. So if we have distance, there's one unit for that. If we have volume, there's one unit for that. If we have density, there's one unit for that. And oftentimes, these units are inconvenient sized units. So we may want to adjust them. So the SI units are algebraically consistent. What we mean by that is if you use SI units in an equation, if everything that goes into the equation is in SI units, then you are guaranteed to get an SI unit as a result of the equation. And that's extremely handy. That's really the primary reason that we worry about SI system. Now, it is the case that SI units are sometimes inconveniently small or inconveniently large, and so we introduce the metric system of units that allows us to change the size of the unit according to what's convenient for our measurement. And we always adjust the size by powers of 10 when we do this. The resulting units are referred to as metric units rather than SI units, but they're built on these fundamental SI units. Table 1.4 in our textbook shows a complete listing of all of the SI fundamental or base units. These are the units from which all of the other units for physical quantities are built up. These are the building blocks, if you like. And you should note in particular that there are only 7 of these units. This is a complete list. There are no other base units. Okay, of these 7 base units, we don't really need these last 2. So what I'm going to ask you to do is memorize these 5 base units for first quarter general chemistry. Note in particular that in this table 1.4 in the textbook, they incorrectly say that SEC is an abbreviation for second. That is not the official abbreviation. It is just an S. And note that the abbreviations, all of the abbreviations, the capitalization is important. So kilogram is kg and not capital Kg. And it's really your job when you write out a unit to make it clear whether it is capitalized or not. Capitalization plays an important role in SI units. Typically, only those units that are named after people are capitalized and other units are lowercase. Once we know the fundamental or base SI units, we can build up the one and only SI unit for absolutely any other quantity that we're interested in from its formula in terms of base quantities. So for example here, if we look at speed, we have an equation for speed as distance divided by time, and we can use that to tell us what the SI units for this has to be. So distance, we know the fundamental SI unit for distance is the meter. We divide that by the unit for time. The unit for time in the SI system is the second, and therefore the one and only SI unit for speed is the meter per second. Notice that this is not a base unit, it's a combination, an algebraic combination of the base units, but it's still the one and only SI unit for speed. Similarly, if we want to look at volume, we have an equation for volume in terms of length times width times height. It doesn't matter which equation we use. We could use the volume of a sphere if we wanted. We'd end up with the exact same units, all you have to do is find some equation that gives us volume in terms of base quantities, and then we can use that to come up with our unit, which, let's see, length would be measured in meters, width would be measured in meters, height would be measured in meters, and so our one and only SI unit for volume is the meter cubed. Similarly, if we go to energy, come up with some sort of equation for energy. Again, it does not matter which equation as long as it's a correct equation. Here I'm using the equation for kinetic energy. You don't need to memorize this at the moment, but I looked this up. Kinetic energy is 1/2 mv squared. The m stands for mass. The v stands for speed. 1/2 is just a number. It does not have units. So when I come up with the units for this, 1/2 has no units. Mass, of course, has units of kilograms. Speed, we just said, has units of meters per second. And because the meters per second is squared in this formula, that means we have to square our units. So our units for energy are the kilogram meter squared per second squared. And that is the one and only SI unit for energy. Temperature in the SI system measures absolute temperature. So it measures something from what we call absolute zero. So absolute zero is the zero of the temperature scale, 0 Kelvin. That is the lowest physical temperature. There are no temperatures below absolute zero, the coldest anything can possibly get. So if we measure from 0 Kelvin, we get temperature in Kelvin. The Kelvin unit is the same size as 1 degree Celsius, but it's shifted because it starts at absolute zero instead of the freezing point of water. Degrees in the degree Celsius scale, degree indicates a relative scale. It's relative to some arbitrarily chosen zero for the scale, which in the case of degrees Celsius is the freezing point of water under normal atmospheric conditions. Density we're going to be using quite a bit in chemistry, so this equation you definitely need to know. By the way, you do need to know how to convert from degrees Celsius to Kelvin. We're not going to use it right away, but when we do, you'll need to have that conversion memorized. Anytime we have some new equation like density equals mass over volume, which I assume you've seen before, you should be able to calculate any variable in that equation. So mass in this case would be density times volume, or equivalently volume is equal to mass divided by density. Any algebraic rearrangement of this equation is fair game, and I should be able to assume that you can use any variant of the equation. Now, some densities are given in table 1.6. I'm not asking you to memorize this table by any means, but it is useful to know that the density of water just on a relative scale is about 1 gram per cubic centimeter. Remember, 1 cubic centimeter is the same thing as 1 milliliter. So this would be the same thing as 1.0 grams per milliliter. And that just gives you sort of a signpost, a comparison that you can compare densities of other things to. These substances here, air and balsa wood, that have lower densities are going to float in water. Things that are heavier than 1 gram per milliliter are going to sink. We all know iron sinks in water, and that's how we can tell. Table 1.5 in your textbook gives you a list of common metric prefixes, and I'm going to ask you to memorize quite a few of these so that you can use them easily. In our class, I'm going to ask you to memorize everything from tera down to femto. So when I say memorize, you need to know what the unit name is, what its abbreviation is with the proper capitalization, and then what the numerical value is associated with that abbreviation. So anytime we use capital T as an abbreviation. For example, in terawatt, what we mean is we take the unit watt, whatever that is, don't worry about it right now, and we multiply it by 10 to the 12th. If we were to take milli as our abbreviation, a milliwatt is 10 to the minus third watts. So this gives us a way of changing from SI units to a system of metric units associated by powers of 10, and we pick whichever unit is the most convenient for the measurements that we're using. That's the whole point here, is to provide a different set of differently sized units purely for our convenience. Finally, in chemistry, we often use some non-SI units for volumes simply because they're convenient for our lab use. You should know what a liter is. Liter is 1,000th, or 10 to the minus 3 cubic meters. Remember that cubic meter is the SI unit. It's just that a cubic meter is too large to be convenient in lab. And frankly, we use very small volumes very frequently in lab, and so milliliter is going to be one of our most commonly used units. And you should know not only is a milliliter, according to the metric prefix system, 10 to the minus 3 or 1,000th of a liter, it's also equal to 1 cubic centimeter. So if we had a little cube, if I can draw a cube, which is questionable, and it was 1 centimeter on each side, the volume contained in that is 1 milliliter, or 1,000th of a liter.